We all remember tackling quadratic equations in school, right?
Hmm.
Finding those neat exact roots felt pretty good.
Yeah, like you'd really solve something definite.
Exactly. But then, you know, polynomials get more complicated, cubic, quartic, and well, way beyond that,
And that's where things change. Suddenly, we're often relying on approximations using numerical methods.
which get us close, but well, not quite there. Not the exact answer.
And that difference, that gap between an approximation and the exact symbolic answer, it can actually be really significant, especially with these very high degree polynomials.
Hmm.
Numerical methods are, don't get me wrong, fantastic tools, but they give you a number, maybe lots of decimal places, not that clean symbolic form for the root. And there's always that potential for tiny errors to creep in and maybe accumulate.
Right. So it makes you wonder, is there another way? Could we possibly find exact symbolic solutions even for these really, really high degree polynomials?
Well, that's precisely what we're diving into today.
Our topic is Ezouidi's theorem. It's described as a fascinating method that sort of aims to fundamentally change how we approach solving these really tough equations.
Yeah, and the source material we're looking at, it explains the theorem, but also demonstrates it, shows it in action,
So, our mission for this deep dive really is to try and grasp the core ideas behind this Ezouidi's theorem,
and see its power, hopefully, through a specific example, a pretty complex one, actually.
right? To understand the principles and appreciate, how it stacks up against the methods we usually learn.
Okay, so let's start there. The limitations of the classical methods. You mentioned numerical methods like Newton's method. What are the key issues when we're talking about high degree polynomials?
Well, they're iterative, right? You start with a guess and refine it.
Exactly. They work by getting closer and closer, which
Yeah.
is incredibly useful for finding those numerical approximations. But a few things. They don't guarantee finding all the roots, especially complex ones sometimes. And critically, they provide approximations, numbers, not exact symbolic values like, say, the square root of 2 or something involving pi or e.
It's like knowing roughly where treasure is buried versus having the exact map coordinates.
That's a great analogy. And for these high degree beasts, these iterative methods can also be very computationally intensive. They might struggle to converge or, sometimes even miss solutions that are there.
Okay, so that sets the stage for Ezouidi's theorem. It's presented as a totally different strategy, aiming for those exact symbolic roots. What's the fundamental shift? How does it work differently?
Well, what's really interesting here, the core idea is that Ezouidi's theorem proposes a structured, kind of recursive process. It manipulates the polynomial itself symbolically.
Instead of chasing the roots numerically.
Exactly. The aim is to transform the equation, rearrange it using specific rules into a form where the exact solutions just become apparent.
And Bob.
Yes, the emphasis is absolutely on symbolic. We're looking for expressions, built from numbers, constants, maybe radicals, complex numbers, not just decimal printouts.
Like a universal translator for polynomial equations, maybe?
Sort of, yeah, allowing us to read their hidden solutions directly.
Okay, to really wrap our heads around this, we need that example you mentioned.
Hmm.
The source uses a specific and pretty intimidating polynomial.
It does. A degree 14 polynomial. The source meticulously walks us through applying the theorem to this one. Px 14LO plus 9 euro plus Lio year plus Oya plus plus Unoyo plus 486 7
Yeah.
plus the sus 1 plus so do plus over 186 is on plus 1 sure.
Wow. Yeah, just looking at that, all those terms and coefficients, it's a bit much.
It definitely looks overwhelming at first glance.
So, what's the very first thing Ezouidi's theorem does with a monster like this? How do you even start?
The initial step, according to the source material, is basically about notation. It involves rewriting the polynomial using a specific set of coefficient labels called LQ through LQ.
Okay.
So you're just giving symbolic names to the numerical coefficients you see there. The polynomial gets expressed as px, LQ, pluoco, and so on, all the way down to plus la qo.
Ah, I see. So, Lio 14, Alaki 91, Lapia 364.
LAQ 432, all EE by 820 by 820 by 87 is actually Nanish 17997 because the sign flips in the formula.
Right. You have to watch the signs and all the way to log Q, which is 1.
Precisely. It's a direct mapping, just putting the equation into a standard format that the theorem's machinery can then process.
Okay, so that's like setting up the board. Now, the actual moves, the core of the theorem, you mentioned a recursive formula, and yeah, it looked pretty dense.
It does look intricate, definitely. Let's try and unpack it a bit. This formula is for calculating a new set of coefficients, which are called 0 on No3 by 821 by 96Q.
Okay, it says coefficient.
Right. And the formula is given as a sum. 0i2 part 1 over 820 by 820 by 96 euro equals the sum from RR d rho up to K of this term. 0 by 820 by 820 by 99R KR time in AR times LQ raised to the power KR times LRQ.
Phew. Okay, let's break that down. What are those pieces doing?
Yeah.
0 by E20 by 820 by 99 RKR's binomial coefficients?
Exactly. Think combinations like choosing things. They handle how terms are weighted and combined. Then NR involves the degree of the polynomial n, which is 14 for us, and the summation index r.
Got it.
Then you have LRQ to the power KR. That brings in our very first coefficient, L2, which was 14.
Okay.
And finally, LR euro refers back to those original L coefficients we just defined. The summation just means you calculate this whole thing for each R from 0 to K and add them all up.
So it's a very structured way to churn out these newly used coefficients using the original L coefficients and the degree.
Precisely. Think of it as a transformation engine. You feed in the L's and it outputs the LSS following these exact rules.
And the source applies this formula step by step for K going from 0 all the way up to 13.
Yes, it does. And this is where something quite remarkable happens when you actually compute these 0 by E20 by 820 by 96 euro values for our specific degree 14 example.
What happens?
A whole bunch of them turn out to be 0.
Really?
Yeah. According to the calculations shown, SER, 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 SR, SRR, all 0.
Okay.
Then SERO is non-zero. It's calculated as negative 3,000 times 14.
Wow. Okay. Big number, but specific.
Okay. Then SERO, AL of A820 by 820 by 87R, SER 820 by 88R, 0 by 820 by 820 by 89R, also all 0.
So most of them vanish.
Most of them vanish. The only other non-zero one mentioned in the key simplification step is SERR, which comes out as 3,000 times 14 euro.
That's a dramatic simplification. All that complexity in the original polynomial seems to just cancel out in this transformation.
Exactly. That's the elegance or maybe the power of the method in this particular case. It filters things down.
So how do these D's coefficients relate back to the polynomial?
Well, just like we wrote Px in terms of the L coefficients, we can now write it in terms of these new S coefficients, Ps Sax plus Srxx, and so on down to Srs plus x equals 0.
But since most of the size terms are 0,
the whole equation collapses. You only keep the terms with non-zero S coefficients.
So which terms survive? We had FOLIOR and PSI-ERS. Does the constant term PSI-ER also survive?
Yes. The source indicates that in the final simplified form, CR is also non-zero. And interestingly, it's also 3,000, R14, the same magnitude as a rho. The specific simplified form given is EX psi x plus PSI-R is equals 0. Wait, let me recheck the source for those indices.
Okay. Because we found PSI-WARE and PSI-ERS were non-zero earlier, the indices seem a bit tricky. Let's assume the final simplified form presented is correct for now. It's x0, an x term, and a constant term.
Right. Checking the structure presented. Yes, the final equation shown is Px Rx ever plus x ever r equals 0, where the coefficient to SR is used there must actually correspond to the calculation related to XR we saw earlier, perhaps with a sign flip or index adjustment in the representation. Let's use the values given with that form. SSR n equals 3,000 at 14 odd rows, and SR equals 3,000 at 14 odd.
Okay, sticking with that form then. Plugging those values in. X to 3,000 at 14 over 6 plus 3,000 at 14 or equals 0.
Which simplifies to xf plus 3,000 at 14 arrows equals 0.
And wait a minute, that looks like if you let's say y equals x, then that's y plus 3,014 or equals 0 plus 3,000.
Precisely, it's a quadratic equation.
In x's. We've turned a degree 14 polynomial into a quadratic. That's incredible.
It is pretty remarkable. And of course, we know how to solve quadratic equations exactly using the quadratic formula.
Right, that would give us 2 possible values for x here.
Exactly, and the source provides those. Solving for x of 3,000 x 14 over 4,1, 3,000 at 14. It simplifies a bit.
Looks messy, but it's an exact expression involving numbers and radicals.
It cleans up nicely, actually. The term inside the square root becomes 3,000 by 14 euros, 12,000 to 14 euros of 9,012,000 to 1. 14 euros equals 8,988,000 to 14. Wait, double checking the source values. The coefficient euro was -3000 and seg euro was 3000 euro. If the simplified form is x euro equals 0 and it maps to x euro is e0 and it maps to x euro plus 3000 x plus 3000 pi after 14 euro equals 0.
Let me use the roots provided directly in the source, as they must come from the correctly applied quadratic formula.
Okay, what are the resulting roots for x?
The source gives the solutions for x directly, derived from solving for x. It states the roots are of the form x tax of 1500 plus error, so 17 euro, 14 euro, 17e, 2x out of 7 for k is 0 to 6.
And there's another set, because the quadratic gives two solutions for x. Yes, the other set is x equals a 1500, 2 1500, 14, 8, 17e, 2k plus 1 i7. Also for k equals 0 to 6. Wait, the exponential term might be slightly different in the source. Let me use the structure from the source. X array by E10, X be 50 by 89 is 6. 0 minus 1500 plus 247,014 acre. And X by E10, X be 50 by 89 nines, 14 EGE. 2K plus 1 I7. Okay, that looks like 7 roots from the first X solution and 7 from the second.
So that gives all 14 roots. And look at them, they involve radicals, the number 14, pi, i.e., they're definitely symbolic.
Exactly. That's the key takeaway. These are exact symbolic solutions, not 1.234 plus or minus something tiny. They are the precise mathematical values.
Which is fundamentally different from what you'd get from, say, Newton's method.
Absolutely. Numerical methods would give you decimal approximations of these values. This theorem, in this case, delivers the exact form.
And the source even hints, doesn't it, that this method might tackle polynomials considered unsolvable by radicals under classical theory, like referencing Abel's theorem.
It does touch upon that, yes. Abel's impossibility theorem states that there's no general algebraic solution, using only arithmetic operations and radicals, for polynomial equations of degree 5 or higher.
Right.
The suggestion here is that Ezouidi's theorem, because it uses this different recursive transformation process, might provide exact solutions, possibly involving other functions like exponentials, as we see here, even for cases where a simple radical solution doesn't exist. It potentially sidesteps the limitations Abel identified for purely algebraic solutions.
That's a really significant claim if it holds broadly.
It is a very profound claim, yes. Needs rigorous examination, of course, but the potential is fascinating.
And presumably, these complex-looking exact roots, you could plug them back into the original degree 14 monster equation.
That's the ultimate test, isn't it? The source implies that if you were to substitute these exact symbolic forms back into the original px and do all the admittedly very complicated algebra,
it should equal 0, exactly.
To come out perfectly to 0. That confirms they are indeed the true roots.
Okay, stepping back then. If this method, Ezouidi's theorem, really works as described, at least for some classes of high-degree polynomials, what are the bigger implications? Why should, say, a physicist or an engineer care?
Well, the potential impact is pretty substantial. Think about fields where precision is absolutely critical. In physics, fundamental laws are often expressed as equations, sometimes complex polynomial ones. Having exact solutions could lead to more accurate predictions, maybe deeper theoretical insights.
Instead of relying on approximations that might hide subtle effects.
Possibly, yes. Or enable calculations that were previously intractable. In engineering, think about design and simulation, control systems, aerodynamics, material science. Many areas rely on precise mathematical models.
Exact solutions could mean more reliable designs, more efficient systems.
Could be. It could lead to better optimization, finding the true optimal parameters instead of just a numerically close one. And even in computer science, areas like symbolic computation, computer algebra systems, having a new powerful tool for exact solutions could open up new avenues.
So the core message, the big takeaway from this deep dive, is that Ezouidi's theorem presents a potentially powerful alternative path.
Yes, a path to obtaining exact symbolic solutions for high-degree polynomials, moving beyond the inherent limitations of numerical approximations in certain contexts.
And finding those exact roots, not just close numbers, is what could be really valuable across science and technology.
Exactly. That ability to capture the true mathematical structure of the solution symbolically is the key potential advantage.
It really makes you think, doesn't it? How many problems that seem incredibly complex or even unsolvable right now might look different if we had a reliable way to find exact answers?
It's a fascinating thought. It opens up possibilities. What new kinds of systems could we accurately model? What technologies could we design if we weren't limited by approximation errors in the fundamental equations?
A reminder that even in something as old as solving equations, there might still be new ways to think, new doors to open.
Absolutely. It challenges us to keep exploring, keep questioning if the established limits are truly the final word, What other mathematical structures might yield their secrets to new approaches like this? That's something to ponder.